Welcome, folks, to our March 14th meeting of our Instructor Training Center class for Introduction to Networks. Sorry for the break last week. We had our state conference and the NCCIA conference, so we needed to go to that. Today, we'll go through a couple things very quickly. In fact, I'm going to jump through Chapter 3 and Chapter 4 extremely quickly because I believe most of the materials in Chapter 3 and 4 will be something that's pretty well known to you. Then I'm going to send you an assignment to watch for next week, which is a chapter on IP addressing, which is from the old curriculum, but still, it's not like IP addresses have changed all that much other than version 6. But we'll be looking at IP addressing version 4, and we're going to be looking at what I call traditional or standard subnetting first, because I firmly believe you need to learn that before we get into variable length subnet masking, which is one of the major concepts that we will have for you to learn in this particular course. By the way, if I was going to stress anything in Introduction to Networks, the concepts that typically I try to stress are, one, basic network communication and network models, which we will talk about those models today a little bit, the OSI and TCPIP model. I also stress IP addressing, IP addressing, IP addressing, IP addressing, okay? The number one thing you take out of Introduction to Networks is IPv4 and IPv6 addressing. You must understand those. You must know how to do that. And you must know how to subnet, both what I call standard subnetting and variable length subnet masking. And you really need to do that, and that's the main concept for Intro to Networks. And then outside of that, we also need to get into basic router and switch configuration, which is now part of Introduction to Networks. So let's jump forward here and talk a little bit about network protocols and communication. Now, the big thing here is this particular chapter focuses on what is a network protocol. Well, one of the things, if anyone's ever been in the military, one of the things you learn is protocol. I haven't been in the military, but I work with many, many guys who have. And I've been on military bases and have taught on military bases. And I understand that if you see the CO walking across the base, you don't walk up to them and go, "Hey, what's up?" That's not going to work. There's a protocol. There's a method. There's a standard by which you interact in the military. There are classes on protocol. There are protocols that we have in human communications. If I look at you and go, "Huh?" You know by the rising inflection of my voice, in almost every language except for a couple that are that humanity use, that a rising inflection at the end of a word or sentence or statement is a question. And we know that because that is a known item or a protocol or a standard that we use. In order to transmit items from either one person to another or from one computer to another, we need to be able to take the information being transmitted, encode it in some way, send it across a media or medium, and then decode it on the receiving end. The ways we do that are through protocols. And that is, honestly, a protocol is nothing more than a set of rules, all right? Now, humans' communication between governed rules is very difficult to understand, and basically, they're showing you that if we don't use rules, such as the rules of the English language, we cannot understand easily communication, okay? In this case, they actually jump between English and Spanish and several other languages, so it's extremely difficult if we don't use a set of rules. Computers are the same way. Computers must have a way of encoding the messages, encapsulating, de-encapsulating the messages, agreeing on message size limit, agreeing on message timing, and delivery options. All of those are built into our encoding or into our protocol suites or stacks. I'm not going to go through this one, but it's really good. Look at how you encode information, take a picture, turn it into a series of packets, send it across, and then the destination decodes it. We're going to get more depth in that as we go along. This is an excellent item right here because I want people to realize that when we look at encapsulation, we are going to need to do a couple things. One, we break the message or we break the item down into smaller pieces. We then need to put some type of addressing information on that. So in this case, we've got a letter that's going to a member of a household, Dear Jane, okay? And we're sending it by taking that letter, all right? And we see there's destinations, so there's a recipient destination, so location. There's a sender source location, which is here. Salutation is another level of indication who this letter needs to go to. Okay, Then we get all the way through content and all down into basically in the frame, which is by, those types of things. So this is showing an example of an item that everyone's probably, well, most people have done. Honestly, with some of our students, it may not be true. They may have never sent a letter in the mail. But even with an email, we know we got to put a sender's email, destination email, a subject, and other items. So all of those are the same as what we do in our protocols. Message size really depends upon the media or medium it's being sent across. For us, for computers, we have to decide upon the media or the size of the message. Otherwise, the receiving end will reject it. And it all depends upon the media or the medium that you're going across. Frames that are too big or too small are considered to be damaged and will be dropped. So typical on Ethernet is about 1,512 bytes is what's there. So we got to look at some things called access methods. How do we access the network so that you don't have collisions? Two people try to talk at the same time. We both know to stop and let one of the other people go. Well, in computer networks, we've got to have the same thing. We've got to have an access method that allows you to not have collisions, that allows the devices to know when to send, that allows them to see when there has been a collision and do a retransmission if needed. We need flow control. In other words, how much information can I send, how quickly? Is the receiving end being overwhelmed? If so, then we can back down. Flow control can be handled by things such as sliding windows in TCP. Now, when we look at delivering communications, especially in a network world, there's a couple different ways we can do it. And that would be, one is unicast. Okay, unicast is from one sender to one receiver. That is unicast. Multicast is from one sender and then broadcast out to some members of a group. You'll learn that with multicast addresses, devices join multicast groups, and communications can be broadcast or multicast out to that one group. That is a multicast. And then broadcast is one to all in the group. So when we look at computers, they do the same thing. So a unicast is from one source to one destination. A multicast is from one source to some members of a group. And then broadcast is from one source to everyone. Okay. Now, I usually teach my students that broadcasts are bad. And in general, that is true, because we will learn that broadcasts have to be looked at by every single member of a particular group. However, you can't do away with all broadcasts. That's not realistic on most modern networks. You're going to have some broadcasts. Now, one thing you will hear sometimes mentioned is a protocol suite, or you may see it written as a protocol stack. And really, that is a group of protocols working together to perform the communications task. In other words, to allow information to be able to be sent from two different hosts to one another. We're going to learn about different layers, physical layer rules, data link, network, so on and so forth, transport, segment, and on up. We're going to learn about those different levels, but basically a protocol suite is a group of protocols working together. Really, the one we're going to be using is TCPIP, let's be honest. TCPIP is a protocol suite made up of multiple different protocols, such as IP, TCP, UDP, there's ICMP, there's DNS, there's all different types in the TCPIP protocol suite. But network protocols are used to perform this communication standardization, really, is what it is. Because once we agree upon we're running TCPIP version 4, everyone agrees. Remember our last chapter we talked about an IP address. Everyone agrees you're going to have at least an IP address on the subnet mask. That's part of the rules. You got to have that to be able to communicate. You may also have a default gateway, especially in a network such as this, where you're going to need to get across this internetwork to another part of your network. Okay, so we're going to move on here. Any questions? If there are questions, John, please type it in. I'll try to respond. But here we have Protocol interaction, we have at the application layer. By the way, the TCPIP protocol suite consists of 4 levels, and I'll teach my students to remember this by saying AT-N, okay, or A10, application, transport, internet, and network access. One of the things that they show here that I want to make you fully aware of is that at the network access layer, which really translates to the data link and physical layers of the OSI model, TCPIP has no protocols defined. That was one of the genius of TCPIP. They did not define a hard set rule for what had to be run at data link and physical layers, which means you can run TCPIP over Ethernet, 10 gig Ethernet. You can run over 100, 1 gig Ethernet, 100 megabit, 10 megabit. You can run it over Wi-Fi. You can run it over multiple types of data link and physical layer protocols because you didn't define it as a hard set definition. Now, at the internet layer, which is the network layer of the OSI model, we do have the internet protocol, which is part of the TCPIP suite. That is the protocol responsible for routing and for path determination. It is a connectionless protocol. At transport layer, you actually have 2 different protocols. In this case, they're only using TCP because it is this is an HTTP or a web traffic communication. And HTTP runs over TCP. So you see, these are multiple protocols in the stack or the suite. That's why sometimes you see it mentioned both ways. In the stack being used for this PC to go to this web server, request a web page, and have that web page come back. Okay. So here we see some of the protocol suites and industry standards. TCPIP, we've got HTTP, DNS, DHCP, FTP, ICMP. Some people put ICMP down here at the internet layer too, but ICMP is part of it. You've got other protocols in the TCPIP suite at layer at the application layer. TCP and UDP. TCP, or Transmission Control Protocol, is used to allow for guaranteed reliable delivery. Items that must be guaranteed and reliably delivered, such as web traffic. UDP, or User Datagram Protocol, is TCP's unreliable little brother. It is used for unreliable and any type of traffic that needs to be delivered quickly, like video, voice, those types of things. IPv4 v6 runs at the internet layer, and then down here you see all these different network accesses. Now, folks, you can take ISO, AppleTalk, Novo Network, and pretty much chuck them because they're not being used. In the world today, TCPIP version 4, version 6 are the two protocol suites for the foreseeable future that we will be using. So you can see TCPIP has been around a very long time, okay, all the way back. You look here back in 1969, the first message was sent. You're looking here, 1991, the World Wide Web was actually released. Folks, I can remember paying for a browser. I actually bought Mosaic. Paid money for a web browser. Now imagine that. My, how the world has changed. IPv6 was first actually released in 1995, and we still have not moved to it. So you can see how long it's been since it's there. First IPv6 world day was there. Folks, I can tell you right now, everything runs on IP now. If you've heard anything about the Internet of Things, we're developing more and more items that need an IP address. It's really pretty unbelievable what all's going on. So it's amazing and unbelievable. So here we see the TCPIP protocol suite and some of the processes that it allows. The application layer, where we have protocols such as DNS, probably one of the single most important protocols. Without DNS, 99% of the World Wide Web quits working. In fact, couple months, years ago, there was a DNS attack that took down part of the East Coast. There was one of the reasons we didn't have class the last time we were supposed to meet is because someone at Amazon typed the wrong key. They actually put one wrong character and ended up taking down a large portion of their Amazon Web Services, and it was greatly impacted a large part of what holds the Netacad, because you'll see right here, Amazon Web Services. So this course lives inside the Amazon Web Services ecosystem. And so when their servers went down and they lost capacity and had to reboot, Netacad became unreachable, or at least became very unstable. So those are the types of things we've got. We've got BootP, DHCP. Those are protocols we talked about in the previous chapter. FTP, which is file transfer, TFTP, HTTP, SMTP. These are our protocols for mail. So students can click here and see. BootP, by the way, was the way that old diskless workstations used to get their IP addresses. And you had a MAC address, and you would have a table that would then give you the IP address based upon the MAC address. DHCP is the way we get IP addresses dynamically today. Down here we got IP, and that's both version 4, version 6. They both are at the internet layer. Routing protocols. ICMP, Internet Control Message Protocol, which is available. The door's kind of opening on its own, a little weird there. This protocol suite that almost everything is using these days on the internet. So what is the process? Now here's one of the things I want you to realize. When you go to encapsulate something, this first header, which is our data link header, really is dependent upon what data link layer protocol you're running. In this example, they're using Ethernet. So one thing you will learn is this Ethernet frame is going to contain what we call our hardware addresses, or MAC addresses, media access control addresses, which we talked a little bit about in previous chapters. But the destination MAC address and the source MAC address would be in the Ethernet portion of the header. And then there is at the end of an Ethernet frame a CRC, cyclical redundancy check. We see here the animation. We're going to try to make it, we're going to go and we're sending information from this web server over to the client. So that's the data in this particular packet. We then have to put what type, TCP, in this case it's a TCP connection going to port 80 because it's actually be going to the destination port of this client, the source port of 80. Source and destination IP addresses. The source address would be this web server, destination would be the client, and it would be sent over as 1s and 0s to the client. And then what the client has to do, the client has to de-encapsulate this message. So it takes it in, looks at the Ethernet portion and says, is this for my MAC address? If the answer is yes, it will strip off the Ethernet header, run the CRC to ensure that the frame was not damaged in transit. If the CRC check is successful, it will then rip off the data link information. Okay, so it rips that off and will then go to the IP header. It will then look and say, okay, is this the destination IP address? Is this my IP address? So the web client saying, is this for me? If the answer is yes, it will then rip that off and then look at TCP and go, oh, so this was that response from my request for the web page, and it will take the transport header off and then we'll pass it up to the application layer, and then the application layer will handle it through HTTP, and using the HTTP protocol will display the web page that was requested. Now here's the crazy thing that most people don't realize. This is happening every time you open up a web page. So if I click anything that's a web page and I go to a web page, so if I click here and go to cisco.com, all of that saw how fast it happened. There had to be multiple things going on. There could have been a DNS request to find the IP address that matched this www.cisco.com. There was then a packaging of a frame that was sent to my default gateway that was requesting this page, and then that went all the way out to the closest Cisco server, wherever that happened to be, that could respond to this, and was sent back to me in fractions of a second. Now that's assuming nothing was cached anywhere, which we don't do a lot of that anymore, simply because most web pages are so dynamic that it's not a good idea to cache them. It's pretty amazing that this stuff even works. So what are some open standards? Well, obviously IEEE, IETF, ICANN, all of these develop open standards. TCPIP is an open protocol. Okay, and here we kind of see how the ISOC report or has the IAB, Internet Architecture Board, underneath it, which has the Internet Engineering Task Force. And then they come up with working groups, and those working groups can put out RFCs. Okay, and there's also even a research group too. That's for long-term research items. And then INA and ICANN are who hand out IP addresses and numbers. So that's where you can get IP addresses. And of course, IPv4 addresses are gone. There are no more of those available really. So EIA-TIA standards are standards such as cable standards 568B and telecom cabling items that have been set up. We do have a lab on that. It's just a paper lab where we go out and do some research on these organizations. Now, this is one of the key concepts of Introduction to Networks, and it's how the OSI model maps to the TCPIP model. Now, I also want you to realize that the OSI model was the 8023 model, which was developed by a bunch of engineers, and they were coming up with a model to try to show how do we model communication between two hosts. This model was not designed to be all-inclusive. In other words, none of these models are, especially this OSI model, this model is not, it is a theoretical model, not a practical model, okay? Still, either way, models are good because they do give you a framework to discuss the communication between two devices. They allow for standardization. If I say that something's a layer 3 device, which is a network device, then I know kind of what its function is. It does something with routing. Okay, let's say it's a layer 2 device, and I have an idea of what that is. And it could be switching, something with MAC addressing, depending on whether it's Ethernet or not, but I understand what that device is. That's all possible because we have models. We also have the ability, and one of the things that's very interesting is that the way the models are designed is that each layer provides services to the layer above it and receives services from the layer below it, but does not really know what's going on in the layer above or below it. It's kind of like the Russian doll analogy, where you take a little doll and put it inside of another, and put it inside of another, and put it inside of another. But when you encapsulate information, when you take the network information and encapsulate it inside the data link layer headers, put that header back on it, the data link layer really doesn't know what's inside the network layer. All the information above it just becomes data that the data link layer is transmitting across. So it prevents a single layers change, meaning that you have to rip out the entire protocol stack or suite and redo it. For instance, here's a great example. IPv6 came along. You didn't have to completely redesign TCP and UDP in the application layers because these layers rode on top of the internet layer. They received services from it. So you could just take the internet layer, rip it out, add an IPv6, and then TCP, UDP, and all the application layers above that, application protocols above that could continue to work just like they did before. So this is a reference model. The OSI model is a reference model. It's how we look at a theoretical communication between two devices. The protocol model, TCPIP model, is a protocol model. It is actually how devices are communicating. So you look and see that the functions of the application layer in the TCPIP model look at and perform the functions of the application, presentation, and session layer in the OSI model. The transport layer and the transport layer perform the same functions across these, and the internet and network layers perform the same functions. And then network access is the same as the data link and physical. You do need to memorize the 7 layers of the OSI model. All people seem to need data processing. That's layer 7 to layer 1. Or please do not throw sausage pizza away, which is layer 1 to layer 7. Both those are good mnemonics you can remember for those layers. So what did they do? Well, the application layer provides services to the application protocols or to the applications above it, and they're used for peer-to-peer processes. Presentation allows you to convert information into common representations of data. By the way, you can tell these layers are a little nebulous as to what they actually do. Session layers are used to establish, maintain, and teardown sessions between two hosts. Now, the transport layer is designed to provide segmentation, transfer, and reassembly of data between two end devices. Sometimes we talk about this being where we have reliable end-to-end or guaranteed reliable delivery. That really only depends upon which of your transport layer protocols you're using. If you're using UDP, that's not true. It still does some of these same items, but it doesn't do it in a reliable fashion. Network is where you provide for the ability to have path determination, the ability to do routing is at the network layer. Routers, by the way, are at the network layer. Layer 3 switches work at the network layer. Data link is where you have the break items down into frames, so it deals with framing. It deals with physical addresses, which are MAC addresses. The network layer, by the way, deals with virtual addresses, or it deals with IP addresses, which are not related to anything physical on the device. Okay. And then the physical layer deals with turning things into actual ones and zeros via the whatever the physical media needs. Could be light pulses, could be presence or absence of a current, etc. And you see this application layer in TCPIP model represents data to the user plus encoding and dialog control. In other words, TCPIP model application layer does everything the application, presentation, and session layer of the OSI model does. Transport layer supports communication between various devices. Internet determines the best path, so that's the network layer of the OSI model. And the network access layer is the data link and physical layers. Okay. And again, here they are, key similarities and differences. Any questions on those? I would know this. You've seen this now on three different slides. So I tell students when you see it once, it's important. When you see it twice, it's probably important. You see it 3 times, you better know it. So you've now seen this on 3 different slides in the curriculum. So what do? There's a couple different concepts we need to talk about here. One is segmentation, so taking a big message and breaking it into smaller pieces. This is important because if you have an error during transmission, you would like to be able to send a smaller piece for retransmission, not have to resend the entire thing. Multiplexing also relies on segmentation. In other words, we can break our communications down into multiple pieces and then multiplex across this one line to allow multiple communications to be occurring simultaneously. So that's multiplexing. Interleaving the pieces as they transverse the media. So we take it and we segment our stuff and we use multiplexing to allow it to go across the different items. We then will label those pieces to make sure we know what part or what session they're part of, what communication, and all of that is handled by the transport layer protocols. So what are protocol data units? It is the name of the information at a particular level of the OSI model. So up at the top, it's just data, okay? Once you get down here, it's a segment. So at the transport layer, it's called a segment. At the network layer, it's called a packet. It's a frame at the data link layer, and then it's bits, okay, at the physical layer. So bits, frames, packets, segments, data. Those are important to know. Protocol data unit, again, it's just the name of it at that point in the encapsulation process. So if I say, hey, we've got, the packets that are here, I'm talking about the information when it's right here at the network layer. And it has the network header, transport header, data, and any trailers that would be there. So here's a good example. We go in, encapsulate it. Again, same thing we did before. They're not showing the detail they really need to. That's the data that goes in here. And then we're going to add the TCP information, and it's just what I talked about earlier. So we're going to skip that and go on doing the same thing here. They show it twice. So bits at the physical layer, frames, packets, segments at the transport layer, and then data up there. Again, saw a slide on it, saw it mentioned, now you've had an activity on it. I would know it. Okay. So we have two different types of addresses we've talked about. We've talked about network addresses at the network layer, which are our IP addresses that again are not dependent upon any physical characteristic of the device. And then we have our physical addresses, or our MAC addresses, that are associated with the MAC address of the particular device. They're typically burned into the NIC of a device, or in virtual machines, they're created virtually, which makes for some interesting concepts there, but it does happen. So we have our source IP and destination IP address. Okay. Again, those are two different types of addresses that we have available. Data link addresses are physical addresses, so in the frame, the destination MAC is first, and that just makes it faster because each device has to pull it up and look at it. One thing does happen, you'll notice that as you hop from one router to another router, the destination and source layer 2 information changes, but the layer 3 information will not change unless you're doing NAT or PAT or something of that nature. And that's a key concept. You notice how every single router has to disassemble the packet or disassemble the information and then reassemble it with new layer 2 information. Now, this is an interesting concept, and this is how do devices on the same network communicate with one another. So in other words, PC1 wants to talk to this FTP server. You'll see the source and destination MAC addresses. We're not going to get into a great deal of detail about some of the different protocols being used, but basically here's what would happen. Let's imagine that this host wanted to contact this host. One of the first things it's going to need to know is the IP address of the destination. Now, there's a couple ways you could get that. I could FTP to 192.168.1.9. There could be a DNS entry for ftp.acme.com. That could be there. But either way, once I try to connect to this FTP server, this PC will send out what's called an ARP request. An ARP request the address resolution protocol request, tries to find the MAC address from the known IP address. It would send out an ARP request that said, what is the MAC address, or who has this IP address, and what's your MAC address? Now, because they're on the same network, that broadcast would come out here, and what a switch does with a broadcast, it sends it out every port except the port it came in on. So it would get sent out here, here, and here. Well, that broadcast would be ignored by this link and this link because neither one of those is 192.168.1.9. This server would hear that ARP request and would send an ARP reply and say, hey, that's me, this is my MAC address. It's at that point that PC1 could build a frame and say that the destination MAC is all C's, source MAC is all A's. By the way, MAC addresses are 48 bits displayed in hexadecimal. So we'll talk more about those later. But it will then take its source IP address, destination IP address, and then whatever data it was trying to send. In this case, it should be a TCP, something TCP, because it's going to an FTP connection. All right? So that works pretty well if you're on the same network. The problem becomes, what if the host is on a foreign network or a non-directly connected network? Well, if PC1 needs to get over here to 192.168.1.99, and it sends an ARP request that says, hey, who has this IP address, 172.16.1.99, and what is your MAC address? Well, that broadcast comes here, goes out, and goes over to the router. Well, neither of these two will respond because they don't have this IP address. This router will not pass broadcast. By default, routers do not allow broadcast to pass. But it will see that this was an ARP request for an IP address on a remote network. The router will then perform what is called a proxy ARP. It will actually reply with its MAC address, okay, and say, hey, yeah, the MAC address to get to this IP address is 11.11.11.11, etc. And so it's saying, send it to me. The frame will be sent to the destination of the router, which, by the way, is the default gateway. The source will still be all A's, and then the network IP address, the source IP address is this PC1, the destination is 1.99. That will then come over to the router, The router will do a lookup in its routing table, determine where that network is, where the 172 network is, and if it has a route, forward it over. And actually what it will do is rewrite the data link information to make sure it can be forwarded over to this router if that's where it needs to go, and so on and so forth. This proxy ARP is the only way that we can communicate with remote devices, because our local router, our local default gateway, is proxying its MAC address for a remote host. So again, if it's local, I just send an ARP request, I get an ARP reply from that machine. If it's remote, I send an ARP request, but only the default gateway can reply, because that broadcast will not go all the way across. Now folks, that is chapter 3. And in fact, I'm going to end it with that. Since we only got John here with us, down with chapter 3. I'm going to stop my recording.